Hello everyone, in this video we will be seeing how to use Valgrind to detect memory errors. Let's first start with checking what is Valgrind. So first we'll need to actually install Valgrind. So sudo apt get install Valgrind and enter, then your password. Since Valgrind was already installed in my system, no changes were made, and to run Valgrind you have to enter Valgrind and then the file name that you want to run, but let's not focus on that. First see what is Valgrind and what does the manual say about Valgrind. So man is the command for manual, then Valgrind is the tool name. No manual entry for Valgrind actually, grind. So Valgrind is a suite of tools for debugging and profiling programs, and Valgrind is a flexible program for debugging and profiling Linux executables. That is what is necessary for you to know for now. Like, it works on Linux executable and it's a debugging and profiling tools. Debugging is checking memory errors, and like checking the workflow of a program at runtime. And profiling is like checking how the performance of a program. So the tool we will be working on is Memcheck, which is enabled by default, and to enable it we have to enter --tool is equals to then the tool name. You can also enter any other tool name that you want to use, but we'll be focusing mainly on Memcheck. And let's first create an executable file so you can see how Valgrind runs and what kind of output does Valgrind provides. Demo.cpp, enter, and first close any kind of this. So this is a demo file. Include IO stream using namespace std int main and int a is equals to 45 and cout a and return 0. That's just a basic program, and we'll run it through Valgrind to see what is the kind of output that Valgrind provides and why is it more helpful than running a program without that Valgrind. So let me first pass to its directory desktop, and so this is the directory where we have our code demo.cpp. Let's try to compile it. G++ -g -o demo.cpp, enter. We run it, we get the output 45, but if we run it through Valgrind we get this. Memcheck is enabled by default, a memory checker detector, and we got a heap summary, we got a leak summary. There was something like definitely lost, indirectly lost, possibly lost, still reachable, suppressed, and you don't need to focus on them much now. First let's see what is memory error. Suppose we have an application that have been provided some memory to store its data. So it is divided in two parts, stack memory and heap memory. In stack memory you have all your static data, that's variable, pointer and classes, structures that has been predefined and statically allocated memory, whereas in the heap you have all the dynamically allocated memory by malloc, new and new array. So here you can see int star j points to this memory location and int star node points to this memory block. So if we were to overwrite the address present here, then we won't have access to this memory block. So suppose we created one more memory block and stored its address in node. Now we don't have any pointer that have access to this memory, so this memory occupies some space in our heap section, but it doesn't it is not accessible through any pointer, so we won't be able to free it, and as the program keeps on running, we'll be generating more chunks like this, and eventually we'll run out of memory sooner. So let's first start with creating some memory errors, and then we'll see. Int star a, we'll first create a dynamic memory. Int star malloc size of int into 5, and we'll copy this piece of code. And we'll copy this piece of code 4 times. So we are generating 4 blocks of memory of 5 integer size, and we are overwriting the address present in A. So every time a new block is created but the previous one is not uninitialized, so we are definitely gonna have some leaks in our memory. Let me first specify the header file required to run malloc, that is stdlib.h, and let's compile our program, and there weren't any errors. When we run it, nothing happened, but if we run it through Valgrind, you will see that you have some memory leaks here. Definitely lost 80 bytes, 5 allocations, 0 freeze, and all the memory allocated, and still reachable bytes in memory and all that thing. But we need to specifically know where we wasted all those 80 bytes of blocks in 4 blocks. So let's enter Valgrind. Let me first clear my screen. Valgrind minus minus tool is equals to Memcheck minus minus leak check is equals to yes, and then your file name. So now you will be able to see where was the leak. So here at the bottom of this error you get a stack, that is a malloc initialized memory that you didn't free, so that was the loss, and that memory was initialized somewhere here in demo 6, demo.cpp line number 6, line number 7, 8 and 9. 4 blocks were initialized, 80 bytes was wasted, and it was definitely lost. So let's enter free a Control C. So for every malloc there was a free, and let's see whether we have any error this time or not. Let me first compile my file, and so there was no loss of data, there was no loss of memory space, and there were no leaks in the memory. So let's move to definitely lost examples and indirectly lost examples, and we'll move to some more better real world examples rather than just directly allocating memory and freeing them. Let's work with classes. So we'll create a class named base, and let's provide it with some data, int num, and also with a like constructor base a is equals to num is equals to 46, now we'll create dynamically based memory, like base, then the name of the object obj. Obj is a pointer of base class, new obj. You can also create dynamic memory using a new keyword. So let's repeat the same process again and copy this piece of code again. So this example is just like the previous example, but this time we are using object pointers of a class. So there was an integer present in that class, and we were initializing values to it through this constructor. So let's try to run this program again after compiling, and we got obj does not have a type name. Yes, because we didn't have to write obj, we had to write base. And we got more errors. Mismatch of operator. Yes, we didn't need to write star because that is dereferencing. And yes, now let's see what kind of errors do we get. Valgrind, and bingo, you got 4 errors and you got 16 bytes in 4 blocks, definitely lost. And these are the 4 different losses specified at different places at line number 14, 15, 16 and 17. So that was a direct loss. Now let's see what's an indirect loss. Int star b, and in base you have b is equals to int star, that's an integer pointer, malloc size of int star y, and so what we did was we also created a pointer type that was part of base class, and that pointer creates a dynamic memory using malloc. So if we run this program, there should be actually more errors, not less. See, we have 64 bytes in 4 blocks definitely lost, and 80 bytes in 4 blocks indirectly lost. So let's work with this first error, that is at line number 16. We have 1 block are definitely lost in lost record 5 of 9. You don't need to understand everything. Let's just go here and then you will see that you have loss of some memory in line number 16. So this part, so let's free its memory using delete. Always remember to free your memory declared using malloc, using free, and for using, if you are using new, then you have to use delete. Let's copy this piece of code again, and hopefully this time you will see that you have some change in the error. And once we are done with this, I'll explain to you what I did here. Clear. See, this time we have no indirect loss but direct loss. So I'll now explain to you what is the difference between indirect loss and direct loss. Like when you were not freeing up your memory, you were wasting some memory blocks because some memory was allocated for storing the object of the object size of base. So num and star b, both of them were carrying some, both of them were allocated some memory space, and since you didn't free it, you have a direct loss of data. But this star b is an integer pointer, and this also creates dynamic memory. So if you are not deleting this base class, freeing up this base class, or if you lose contact to this base class and it's part of a memory leak, then you won't also have access to this int star, cause that int star was accessible through this base class. Now you don't have access to this base class, so you won't even have access to this malloc. So now I'll show you how to remove these kinds of error. Clear, and let's compile it first. If you run it through demo directly, there are no errors, but Valgrind detects all the memory leaks, and it will tell you that you have 80 bytes of indirectly loss of data in line number 16, 18, 19 and 20. That is 16, 18, 19 and 20. So we'll first start with this part, this part, this part and this part, and we'll go from direct memory errors to indirect memory errors slowly. So once we remove this, let's not like backtrack like that. I'll show you directly how you can remove this error. Base, that's a destructor, and destructor are used to free all this kind of indirect memory that is created, and you can use free p. Okay, so this is a patch, and if you want to this is the patch, and when you run this you will get no indirect errors. As you can see, there are indirect errors. Wow. Cause we are not deleting that piece of memory, so that's all. Let's first delete. And comment this piece of code. Clear. And we run it through Valgrind. You see that we don't have any indirect loss, but we have a direct loss of 80 bytes. But you will say that I already deleted all the memory that was allocated using this new base. So let's see what the error was. Here you see in line number 11 of demo and line number 19, there's something happening that is wasting 20 bytes of data. So let's see in base constructor line number 11, base constructor, this is, and line number 11 is this part. We are allocating a memory that haven't been freed, so that's why we have 20 blocks, 20 bytes of data wasted. And once I remove this comment, so every time you will call delete, all that dynamically generated memory is also freed, cause destructor is called, and you have to specify here all the dynamic memory that you want to free. And this is how you remove indirect memory errors. See, and let's now move to some other examples of errors like silent memory errors, which is like double free. As you can see, if you run the, we haven't made any much changes in this program, we are just freeing up the same memory space again and again. And if you try to run it, then if you try to compile it, then you will see that there are no errors present. And if you try to run it, you see there is an error, but this piece of code won't tell you much about where the error occurred or what could be the reason for that error. But if you use Valgrind you see it says invalid free delete, invalid free delete, invalid free delete. And if you want to backtrace it to the line where the error occurred, it's like demo cpp line number 15 and demo cpp line number 21, because here the memory was created and here the memory was deleted. So line number 15 is this part where the free is happening, and line number 21 is this piece where you are deleting them. So from here you are making a call to this piece where line number 15 is creating the error. See, so let's remove this piece because we are trying to free the same memory again and again, twice. And now you will see that there are no errors, even direct running won't give any error. Let's see another silent memory error, which is uninitialized value in a and cout a. Okay, so and if you try to compile this program, you won't get any errors. Even if you run it, you won't get any errors. But if you run Valgrind, it tells you that you have uninitialized values. Conditional jump or move depends on uninitialized values. That means you're doing something noisy, something with your uninitialized values. That is in line number 20. Let's see, line number 20 is here, and we are working with variable a. If you trace it back up, you will see you haven't initialized it with the value. And C++, Valgrind, see, we don't get any errors. Every bit of memory that was allocated was freed. And there was one more memory error that Valgrind is able to detect. That is, if you generate memory through new and you try to free it through free, then there won't be any error in the compilation and the program won't provide you with any error here. Or if you try to run it, there were no error in both the places. But if you try to run the same program through Valgrind, you will see that, see, mismatch free and indefinitely lost. You have one block of 20 bytes definitely lost. So here is the error piece of code, and even in the lines it states in line number 20 you have that error, line number 19 you have that error. Let's go to line number 19, line number 20. In line number 20 was the main error and the value was allocated at line number 19. So let's use delete and bingo, no errors again. So the next thing we are gonna see is segmentation faults. If you are like, if you understood all the memory leaks, it's all right. It's like great, and you need not watch this segmentation fault again, cause it's just some basic error. You would be knowing them for now. Like if you try to access a memory that is not present, int star I is equals to null and I is equals to star I is equals to 6. Here you are creating a pointer that points to null, which is an invalid memory address, and you're trying to store the value 6 there, a numeric value 6 there. Let's see whether we get any errors while compiling. No, but if we run this, will we get any error? Yes. Segmentation fault core dumped, but we don't know what kind of error was there and what was the reason behind that error. If we run it using Valgrind, we get invalid write of size 4 in line number demo.cpp20. This is the line number demo.cpp20. There was invalid write of size 4 cause we are trying to write an integer and the memory location is invalid. If we would have run malloc size of int and let's typecast into integer pointer. If you run this now, you won't see any errors, and there is an error. 4 bytes in one block are definitely lost, and in demo.cpp19. Okay, yes, so we didn't free this piece of memory. Free I. Bingo. Now we are done with all the kind of memory errors, but there's one backdrop about errors, that if you have any error in your static memory, then Valgrind won't be able to detect it. For example, int I 10 and int jkl I 11 is equals to 7. All those who didn't understood what I'm doing here is I've just declared some random variables jkl. It's not like really doing anything, but the main piece of code here is this. We created an array of size 10 with the index from 0 to so the index would be from 0 to 9, but on the 11th index we are trying to enter a value that is 7. So let's see whether we will get any error while compiling. Okay, I got an error. Free. And if I run this program directly, stack smashing detected, demo terminated. If I use Valgrind, same thing again, stack smashing detected, process terminated, cause here we were working with stack memory, not heap memory. So that's it for Valgrind, and have fun.